On this dynamical systems playlist, our focus now shifts to numerical methods for dynamical systems. Well, the numerical methods you come across here, they are not too different from the numerical methods you find that I've already treated on my channel. I have 78 videos on numerical methods. In case you're interested, that's numerical analysis. So the goal here is practical implementation of all the things we've been learning. And this lesson covers numerical integration of ODEs, numerical stability, phase portrait computation, continuation methods, bifurcation software, chaos diagnostics. All examples use Python with NumPy, SciPy, and Matplotlib. And in case you want to know more about this, I have them properly discussed under different playlists like numerical, scientific computing with Python. Then, of course, introduction to, I mean, Python basics with EJD. So I have all of that on my channel in case you want to explore these things. Yeah, I mean, just check these things I've mentioned, basically. All right. So now we go straight to the kind of things we need there because we're talking about numerical methods, right? So look at the libraries I'll be using. I already talked about NumPy. So to import, we import NumPy as NP. You know, NP is just an alias. Then NumPy as NP, we have matplotlib.pyplot as PLT. That's for our plots. Then we have SciPy.integrate, import, solve. So we'll be solving initial value problems. Then we also have optimization, and we have a fast Fourier transform using these particular modules like this. Of course, I have to run them so that by the time I want to run the other cells, these ones are already mounted. Okay, good. So they are ready to be used subsequently. So we start with numerical integration of ODEs, which I've treated properly. I think I should really show it. I wanted to show it before, but I thought I shouldn't bother. But I think it's coming up again and again. So go to YouTube. I mean, just go to YouTube and type my name, Emmanuel Jason Dansu, for sure. And then when you come here, come to the playlists, and under the playlist, you'll find what was that? Numerical analysis, right? I have 78 videos on that. Then if you want to know how to use Python for some of these things, you can check out Python Basics with TJ, the 60 videos right there. Then the first attempt I made towards using SciPy, NumPy, and all these things. I think the playlist is still being built. You have 19 videos there on talking about scientific computing with Python. So those can be very useful for you. Okay, so for numerical integration of ODEs now, we consider the initial value problem, dx equals f of t, comma x. This is a non-autonomous system because we have a time component to it. So x of 0 is x, and that's the initial condition. A very good example is when you have dx equals minus x. We can easily solve this to get x of t equals e raised power minus t, right? Especially that I think that's assuming that the initial condition x of 0 is equal to 1, for instance. Okay, that's why we can have x of t to be e raised power minus t in this case. Then we can use the Euler method for that. So the Euler algorithm is simply that xn plus 1 equals xn plus h of f into tn comma xn. Order of accuracy is first order, like you have O, big O of h, like this. Now, I think this Euler method, as simple as it looks, I think it was very helpful, in sending rocket to space. As there's this woman at NASA, NASA maths woman, I've forgotten her name, NASA math woman. Okay. Yeah, Catherine Johnson, exactly. So she was a pioneering NASA mathematician and human computer whose orbital mechanics calculations were critical to the success of early US manned space flights, including Apollo 11. As an African American woman, she overcame racial and gender segregation to compute trajectories for the first American in orbit and the moon landing. So she had such an impact, using. Let me even check out her method. NASA math woman method. Okay. I believe it must have been this Euler method. I think I have a feeling it was the Euler method. Let me see. Um, I hope there's a talk about that. Yes, see, Euler's method. This numerical approach solved differential equations used in orbital mechanics to plot a capsule's trajectory from space back to Earth. So very helpful stuff. So as simple as this method looks, it's such a very useful one like that. So we have the Euler code right here. So I mean the algorithm is already defined. So we just fix up the function comes in somewhere around here, and the solution has already been given. It's x of t equals e raised power minus t like this. So we then have So we define a function f which takes t and x and returns minus x. So the time step is 0.1 and t is 5. So we are taking 5 in total. Then the number of iterations is simply t over this. That's 5 over 0.1. That's 50 over 1. That's 50 time steps. And then we take the t, that's lin space, 0 to t, we divide it into n plus 1 equal parts. And x is, we start with the zeros. The initial condition is x of 0 equals 1. That's why we got e raised per minus t in the first place. And then for n in range, we then get xn plus 1 into x of n plus hf. So this is the Euler described. And then we have the exact solution, which we already know is exponential of e raised by minus t. And then we try to plot the two together and see how that looks. Okay. And for numerical analysis, right, we are interested in the error, but I didn't compute the error here. But I mean, just visualize, you can see that the Euler method for solving the problem and the exact method seem to align closely. But of course, you can see the alignment is not that perfect. And that brings us to some more complicated ideas like the Runge method, which has come to be very useful. So you can see it's a bit more it's more like like they say, it's more like the Euler method, at a quantum level, if you like, right? So you have this kind of expression. So at the end of, you have all this k1, k2, k3, for k4 defined. I now have the function, the algorithm itself, xn plus 1 equals xn into h over 6 for k1 plus 2 times k2 plus 2 times k3 plus k4, and the order is even higher, so fourth order, like that, of accuracy. So and then you write the Runge code. So you can look at it like Euler method at quantum level, like I described the other time. So you define RK4, which is taking f, t, x, and h. K1 is defined as this, K2 as this, K3 is as this, K4 as this, and it returns x plus h into all of this divided by 6. Then you have x, which is the zeros, x of 0 is 1, and all of this. And then you run it. So we are solving the same problem with it, by the way. We are solving the same x exact, which we had before. We are solving the same thing. So you can see now that the RK4 and the exact solution, they align perfectly as compared to the Euler method, where very good result, by the way, but then there's still a bit of gap. But for RK4, it aligns perfectly, right? So the accuracy is increased with RK4. Then you can also use the SciPy solver, for a SciPy solver, we're solving the same problem. So you just do, for SciPy solver now, you have a function t and x, return minus x, and then you plot, you now solve IVP. Solve IVP is what you're using here. So you're solving f, like this. And then if you run that, then this is what that gives you. But here it's not comparing with the exact solution of, so, but I mean, this should be some very accurate stuff. Then we talk about the idea of numerical stability. Okay. So imagine a text equation where we have x prime equals lambda x. That's dx dt equals lambda x, right? So the Euler method is xn plus 1 equals 1 plus h lambda xn. So this will be stable if this expression in here, that's the absolute value of 1 plus h lambda, is less than 1, right, from the Euler method. So we can check that now. So stiff equation example right here, we have so let's say you want to return minus 100x, for instance. So h is 0.05, t is all this, and then we have the function itself, xn plus 1 equals xn plus hf into t and xn, and then we already defined this here. Then you plot this, and you have a kind of breakdown somewhere around here. Okay, so we have that kind of expression around here. So that's us examining numerical stability in that case. So we have some kind of breakdown somewhere. Now we go ahead to talk about phase portraits, which we have done a whole lot. Okay, talking about phase portrait now, if you have the system x dot equals f of x comma y and y dot equals g of x comma y. So you have phase portraits, you have trajectories in x and y space, and then for instance, you have the Van der Pol oscillator. This is another very important thing. Apart from linear maps, we use the Van der Pol oscillator a lot. It's a two-dimensional system which can be converted into it's a two second order differential equation which can be broken down into two first order differential equations like this. Okay, and then for the phase portrait code, we just put it down here. We have a function Van der Pol taking parameters t, z, and mu. Here we have a default mu, except if you change it. So x, y equals z, and it returns y, this y we have here, and mu into 1 minus x, mu into 1 minus x squared that you have here multiplied by y minus x. That's what it's returning. We take mu to be 1. Of course, it's already given by default, but we can change the mu to see what the parameter behaves like. I mean, what the whole thing behaves like. So we have the t-span 0 to 50, we have the limit space. Then we plot the figure right here for x naught in all these things. For y naught in all this, we do that. Then we try to plot. So that gives us this kind of, yeah, it's work of art, kind of. So you have this now. And to vary this now, you can play with this mu. Let's start with, let's go high, 10. So see what 10 gives. Then let's go to 100. It gets to a point where it becomes hard to get any meaningful result from it. Okay, 100 is already problematic. So we may have to, stop. Okay, yeah, this is what 100 gives. And then, so looks like the smaller the value, the better, kind of. I don't know. It all depends on the goal, right? So let's go sub-zero and have like 0 0.1. Okay, so if you have 0 0.1, so see what we have. It becomes uh that work of art kind of thing. So let's go even below that and have like 0 0.01 like this now. Okay. So it's becoming more and more beautiful as we go lower and lower. So what if I do 0 0.001? Okay. Yeah, things are spreading out. So let me go even further. Okay, I like to push the limit to see what happens. Hope this will not take too much time. Yeah, I mean, it comes out pretty fast. So yeah, so we started with 1. Let's stop there. So this is the parameter that controls what happens with the system. Okay, then we can also have the vector field for that Van der Pol thing. So you can see for vector field, and we have x lim space, this y lim space, that we now have a mesh grid. Same, u is y, v is 1 minus x. So still the same Van der Pol, and we run all this. So it shows us so we plot the quiver, and we see that how the whole thing is going. Okay, that gives us the vector field in that case. Then we talk about continuation. By the way, what we considered there was phase portraits, right? So we looked at the Van der Pol and then the associated vector field, which is a sample of the portrait of it. So continuation methods now. So if you solve f of x comma mu equals 0 while varying mu, this tracks equilibria and bifurcations. Example is x cubed minus mu x equals 0. Of course, if you solve this, you get equilibrium points corresponding to x into x squared minus mu. That means that you have x squared to be x squared minus mu equals 0. So you have x equals plus or minus square root of mu. So you have x is 0, x is plus square root of mu, x is minus square root of mu. Those are the 3 points you get in that case. So, and then we can also visualize this here. So it has 3 branches, like we said here. So you're going to have some kind of bifurcation, especially of the pitchfork type, because it has 3 branches at the end of the day. So see what happens in this case. Okay, so you have the x equals 0 and x equals plus mu and minus mu down here. So this produces the full pitchfork bifurcation. So the central branch x equals 0 is the central branch. And then you have 2 symmetric branches for mu greater than 0. So this is plus mu, plus square root of mu, and minus square root of mu. So this is a supercritical pitchfork bifurcation. We've seen whole videos on bifurcation. So if you're interested in some bifurcation software, by the way, you can check this out. You have what the auto, so it's command line continuation to written in Fortran or C, and it tracks equilibria, cycles, and hop points. So if you're interested in this, you may want to check that out. You know, so you have auto, right? That's auto. I hope if I just write auto, it will come. Auto. Okay, it doesn't really come like that. Auto, bifurcation, bifurcation. Yeah, something like this. Yeah, so you can see, okay, I think the repository is on this place. Publicly available software. for continuation and bifurcation problems in ordinary differential equations, originally written in 1980 and widely used in the dynamical systems community. So you have that. Then, of course, we have apart from auto, we have MatCont, which is MATLAB GUI package, interactive continuation, and code dimension 2 analysis. So you can check that out. We have Max, I think that's MaxCont, right? MaxCont. Okay. Oh, is that it? I think, yeah, MatCont, sorry, MatCont, not Max. MatCont. Okay. So, yeah, so you can download that. Matcont is a graphical MATLAB software package designed for the interactive numerical study of dynamical system, focusing on continuation and bifurcation analysis. It computes curves of equilibrium and all that. So you want to check this out if you use MATLAB, for instance. Then we have Python alternatives to all of these things. We have things like PyDS tool, that's Pi Dynamical System tool, I believe. I've not used this before, by the way. I guess it's something I should check PyDS2, or maybe I've used it in some instances. Yeah. So yeah, PyDS2 is an experimental Python-based Python library designed for manipulating HESC DSS database files, hydrologic engineering center data storage system. Files are used primarily in water resources engineering and hydrology to store time series data, paired data, and all of these things, right? That's the PYDS tools. Then we have PyCont. Okay, let's say PyCont like that. PyCont. So what's that? PyCont contains a plotting class that helps keep track of your visual displays. The structure stores the handles of Matplotlib figures and all of that. It validates and generates Python objects from templates and all that. Okay, it's not sounding like something close to that, but it's okay. Then you have Auto 07P interface like that. So let's go move on to chaos diagnostics. Don't forget, we're talking about numerical methods in dynamical systems. So talking about chaos diagnostics now, of course, this is our popular Lorenz system. It's one of the most popular systems we're using here too. So we have this Lorenz simulation. I mean, we've dealt with this a couple of times. So we are talking about Lorenz diagnostics now. So here we want to see um, how chaos goes, right? So for this, I mean, we see all of this. So how do you diagnose chaos? So there was a particular video I had on um, quantifying chaos. And one way to quantify chaos is Lyapunov exponent, which is defined as lambda equals. So the Lyapunov exponent lambda is defined as limit as t tends to infinity of 1 over t ln absolute value of dx of t all over absolute value of dx of 0. And positive lambda indicates chaos, in that case, while negative lambda indicates stability. So you have this now. So you define a function like Lyapunov, which takes system and then x naught and then epsilon. That's that. And then you have t is 50 by default. Then you have x1 is the array of x naught. X2 is x1 plus some random value. T is the link space of this. You solve IVP1, solve IVP2 of the system. Whatever the system is that you search for it, and then you have D naught. So you have D naught, linear programming, blah, blah, blah. You define all of those things. Then you have the Lyapunov, uh, Lorenz 111. So you are dealing with Lorenz because Lorenz is already well defined here. So you have Lorenz here. So the system you are dealing with. So now so what we are calling is this component because the function is Lyapunov system, X naught, and all that. So in this case now, we have the system, which is Lorenz. We have X naught and all this. X naught here is 111. We already have the epsilon and t by default, so we can run that. So this is happening for a Lorenz system now. And when we compute the Lyapunov, we have 0.4258 and all that. And we said positive lambda indicates chaos. So this Lyapunov value tells us we have a chaotic system. Maybe not so strong, but at least it's still chaotic all the same. Okay. For this Lorenz now, it's chaotic. Of course, it's clear from the picture. And then we have another one here. So if you do a scatter plot of this whole thing now, so you see what the kind of thing we have here. Okay. So this is still related to all the XS, YS we had, related to the system up there. Okay. Oh, okay. for I in range this time we have zi minus 25 into zi plus 1 minus 25 and all that. Okay. Then we also have the power spectrum. So you have the power spectrum looking something like this. So these are all things to diagnose uh to diagnose chaos, right? All right. So having talked about all of these things now, we have the summary. We learned that Euler RK4. So if you want to learn more about this chaos diagnostics, you want to check quantifying chaos. It's one of the earlier videos. I think it was video. I'm not sure. Is it 12 most likely, right? You want to check that. So you have different ways of quantifying chaos. In summary, we learned Euler, RK4, and SciPy solver, stability analysis, phase portrait, parameter continuation, bifurcation tools, chaos diagnostics, and the skills gained include solving ODEs numerically, visualizing dynamics, detecting chaos, and studying bifurcations. So we have practice problems as usual. So you want to use Euler method accuracy, to see, you want to see, consider the ODE, dx dt is minus 2x, x of 0 is 1. Implement the Euler method with steps, h is 0.5 and all of that. So you can just take that code and modify. Then you have Runge Kutta versus Euler. You have that here. So use the Runge Kutta and Euler. Of course, most likely, you're going to have RK4 to be more accurate than Euler for sure. Then you have 3 and 4, stability of explicit Euler now. So stability of explicit Euler, see what happens. Then you have dx dt is minus 20x, dx dt minus 100x here. If you have implicit Euler for stiffness, then 5 and 6, you have phase portrait of a nonlinear system. So you want to do that, plot the vector field, compute trajectories for differential or different initial conditions, identify equilibrium points. Of course, you just solve simultaneously and you get all of that. All right. I mean, I think the first way to go is solve this one. Once you solve this, you already see one of the x's is 0, the other one is going to be complex. So maybe you just pick out the x equals 0 part and bring it back here, and y will be 0, so something like that. Then you can do a Van der Pol parameter study here. So see how the parameters influence the system. Then for 7 and 8, now we have numerical continuation, like this, and we have fault bifurcation detection. So you can simulate all this and see what happens here. Okay. Then you have Lyapunov exponent for Lorenz system. Okay, I mean, you have all the standard values. You want to compute the largest Lyapunov exponent here. All right. And the largest Lyapunov exponent has something to say about the stability or chaotic nature of the system. Then point number 10, you have Poincare section and power spectrum. You have all of that right here. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much for doing that. And if you have not, go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. After doing that, you can also become a member of this channel by clicking on join, and that gives you some special privileges, some perks, like getting to see some videos first, or some videos being made for only you as a member, and then we can hang out to discuss whatever interests you on this channel, be it mathematics, data science, data analysis, machine learning, scholarships, writing books, whatever interests you on this channel. Um, Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.